In this part, we're going to look at ionic compound formulas and empirical versus molecular formula. So in ionic compounds, they have this three-dimensional structure because they just repeat over a scale that, like when you go away on a salt, you can't get single atoms of the salt or ions of it. And so these are the easiest ones to get, and you can predict the formula just based on the charges. So if you mix magnesium and chloride together, then we essentially have to find what's the minimum number in order to get a neutral compound. And so if you have one of the chlorides, then you can see that you would have a net 1 plus charge. So 2 plus minus 1 gives you plus 1. So 2 plus minus 1 equals 1 plus. So if we add a second chloride, now we can get neutral. And so that's what we get. We add a second chloride, and this gives us the balance charge neutral. And that's the name game. We just mix them up. So normally what we can do is we can just swap then the coefficients, the superscripts up here, so swap them, and that gives us the charge on it. And there's kind of two caveats to this. One is that if you most of the time we have like 1 and 1, uh, uh, 1 and 2, 2 and 1, these all work. If we have 2 and 2 and 3 and 3, those threes need to cancel because we need the minimum number for it. So you'll find some examples where the swapping doesn't get you the complete answer. And so we can see if we have aluminum and oxygen, aluminum has a 3 plus charge from the periodic table, oxygen has a 2 minus charge, and we swap it, and this is the formula that you should get from it. So the second kind of caveat is polyatomic ions. So in the section before, you learned about polyatomic ions. So you have that subunit kind of charge and that subunit formula. So you would still do the same thing. So let's say we have phosphate, and so this would be a 3 minus charge. We do the same thing. We find what is in an M, and then what we do is we just rewrite it, swapping out X for the formula of phosphate, PO3. And we will put a parentheses around it to make sure that N is clear that it's for all the polyatomic ions. All right, so I don't think they have any examples of that here. Oh, here, polyatomics and formula. Oh, actually, they have some nice pictures here that you might find useful. All right, the other part of this is the idea behind empirical and molecular formulas. And so if you're given a structure, can you just count how many atoms are there? And that would give you the molecular formula. However, what you're going to find when we're solving for these molecular formulas and we start using some techniques, then what we get is a mole-to-mole ratio. And when we're going to get the simplest one, what it gives us, the empirical formula, the simplest ratio of it. And here's a classic example of it. That if we look at glucose here that has this formula C6H12O6, and we can look at the structure of it. This is not, but if we look at that structural formula, that relation in spatial arrangement, then what we see then is this kind of, if we ask what's the simplest ratio, then these are all multiples of 6, going back to that math class that you have. And so then we would divide by 6 and we get this. This is what we call the empirical formula, the simplest ratios of them. All right. And so sometimes you can go forwards from empirical to molecular. You have additional information like the molar mass. We can get the empirical formula that gives us a relationship, but then we get the formula, the mass of that unit, and then we find how many multiples we need in order to get that molecular formula here, or so on. Okay, those are the types of problems you'll find. So solving for the simple ratio in ionic compounds and then converting molecular to empirical formula.